We're going to take a quick look at Altair Embed eDrive's add-on. This example model looks at a sensored field-oriented controller to control both current and speed on the TI lauchpad with the F28049 chip and the gallium nitride three-phase inverter board that plugs into that lauchpad. So here we're at the top level of the diagram from eDrives to do that, and we can drill in to the controller by clicking the right mouse, and we see, if we drill into the diagnostics, that we're doing something called monitor buffer writes. If we drill out by right mousing against the background, we see that we have we have these blue blocks, which are compound blocks you can drill into and out of, and everything in those blue blocks that are contained in there run at the same rate as everything else in the diagram that is colored in that blue way. And if we go to the system properties, we can see the rate at which it runs, which if we put it in kilohertz, it's 10 kilohertz. The red diagonal tells us that this compound block and everything in it is running at the rate of this interrupt, which is an ADC interrupt. It's actually ADC B. There are 3 ADC units on the 0049 part, A, B, and C. And the B unit has 3 items. The other 2 only sample 2, so we're selecting the longest one to give us our interrupt. So we know all the data has been properly sampled before we execute our motor controller. This 100 Hertz diagram is in fact running at 0.01 seconds or 100 Hertz, and it's being cogent as a background thread. That means it's scheduled out of the idle loop. It will run at the 100 Hertz rate as best it can, but it gets preempted anytime there's an interrupt. So low priority jitter tolerant tasks would go in there. If we drill into the motor control subsystem, there we see our controller itself, a field weakening side controller, a switch to control whether we are running with field weakening ID or our standard supplied D term. And there's also a power calculation to know instantaneously how much power the motor is drawing. And this is the encoder angle module. If we drill in there, what we'll see is the actual quadrature encoder block from our target support for TI. And here's how it's configured. You can see the GPIOs, they correspond to the GPIOs as wired on the TI launchpad. And this is going to translate the actual raw encoder tick counts, there's 4,000 ticks on this encoder, into a value between 0 and 1. If we look at the controller itself, we can drill in there. And these are rate limiting ramps here, so that when an ID or an IQ term is changed, it doesn't instantaneously change, which can cause erratic operation of the motor, but it's actually user settings that let you control the rate at which these changes take place. Here's the actual current controller. You can see it takes an ID and an IQ reference, current alpha beta, sine and cosine of the rotor angle, and the inverted value of the DC bus, where unity is considered the nominal DC bus voltage. So that way we can compensate if we get a sag on the DC bus. Here is a switch that lets us know if we're going to run open loop with a frequency controlled integrator as our angle, or we're going to run closed loop with theta coming from our encoder. If we drill into the current controller, here we see the park transform. Here's the PI gains on the D and Q terms. Here's D and Q out. We do an inverse park, an inverse Clark with a third harmonic, and then MA, MB, and MC on the output side are signals that can be fed directly to the PWM. So everything in this subsystem that I've shown you so far is machine independent. It can run on any computer that has a C compiler. Here, this is the ADC and PWM. This is MCU dependent and requires use of the proper ADC and PWM blocks for that target. So if we drill in to the PWM, you can see we have one PWM unit, one for each phase. They're numbered a little oddly, 6, 5, and 3. That just happens to be how the socket for the launch pad works when you have the gallium nitride inverter unit plugged in. And here you can see the configuration of the PWM. It basically lets you get at everything the hardware lets you do. So you can set deadband, you can control, there's two channels, A and B, you control, there's a counter A and counter B for the duty cycle, and you control the waveform that comes out. It can be count up, count down, it can be count up or count down. You can actually change the period dynamically. There's a whole fault handling section, and there's even a digital compare unit. Don't want to get too much in the details there, but it's just giving you an easy way to program the hardware visually. And then if we drill into this phase, this section here, this subsystem, we're going to see our ADC acquisition here and these offset corrections. So when the machine first boots up, it stages a few things. One is it waits for the inverter itself, the DC bus to settle, and then it zeros the PWMs for both current and voltage. There's 3 current sensors and 3 voltage sensors on the gallium nitride inverter. And it does that by putting out a 50% duty cycle during that period and expecting there to be no voltage differential between any of the phases. So it treats whatever that voltage is on the ADC as the 0 point. So anything above that will be a positive, anything below is a negative. Okay, well that pretty much goes through the source code of the motor. So in order to compile this, you go to the top level. And by the way, normally you can navigate levels very quickly. It's a little slow here because the Camtasia software apparently for some reason is slowing down the transitions. Don't know why. I'm going to hit the F2 key because that's a way to jump quickly around the model. So here we are at the top level. So to generate code for just that subsystem, I am not used to the lag introduced by this thing. You select it, and you can hit the compile option there, or the first time you go to the cold gen diagram, And you can set up the optimization of the C compiler, make sure your target is correct, 0049. We're going to use the edge pins on the compound to exchange data. And we're going to hit the compile button. And what that does is generate C code for just the selected subsystem. Runs it through the compiler, as we see here. And it creates an out file. So now we can switch to the we switch to the debug version, and that's going to take that out file, load it, and then communicate it with it interactively. Slide that over. So we'll go ahead and hit the go button here. It helps if I plug in. So after we plug the USB cable into our lauchpad, we can hit go. And what that will do is download the out file into this block, and we can provide values to the block, which were the inputs of the compound block we previously compiled, and look at the outputs. We can display them here. We have some gauges that are interactively showing us what's going on. And on the side, we have the speed we want the motor to spin at. We have ID and IQ that we can set when in open loop mode. There's KP and KI for our controller gains. There's the Boolean to set the speed command on, to set field-oriented control on, which means we'll be taking our motor angle from the encoder and not from an open loop, which right now we're just spinning open loop. So if there's any load on the motor, here I'm changing the motor speed here. Or if I try and motor it too fast without moving up the IQ, it'll stall. So I can just turn on the FOC. Now we're running with the encoder. I can turn on the speed control, and I can move the speed up. If I take the motor, I don't know if you can hear it, spinning right here. Got some tape in my fingers on the tape. I'm moving it nice and slow. There we go. One of the things I can do is pinch it, try and stall it, and you can see, if you look at the gauges, the lower right gauge of watts, you can see how the power jumps up as it tries to overcome the load that I'm putting on it. You can see how the DC supply amps go up. So the full gauge reads 2 amps, so we're at 0.2 amps right now. And if I load it, it gets hot. And the torque meter up here tells us what we're doing, and we're running at about 800 RPM. If I were to turn on field weakening right now, it really doesn't do anything. But if we max the speed out, we can see we're trying to go 3,000 RPM, but we're only here at maybe a little over 2,000. But if we turn on field weakening, boom, we can see our current has gone up, the watts have gone up, but we're almost at 2,400. So it bought us a couple hundred RPM. There, if I turn field weakening off, our supply usage goes down. And you can see, by the way, the rate limiters I spoke about earlier are kicking in, and it's not a jerky change. It's a smooth change up and a smooth change back down. And by the way, the rate of that change is settable. Okay, well, that's a quick look at the eDrive's censored permanent magnet synchronous motor diagrams. Thank you.